We start.
Good afternoon, sir.
Good afternoon. So this is the zTransform table. This is not new to you. You're coming from Laplace, so there you had some experience working with the table, right? This is a different table, but they are somewhat similar. Just want to pick up some of the entries here. Say delta n. This is the impulse, right? One single pulse, impulse rather. The Z transform is just one. We saw that last time. This is un. In fact, this is ut in continuous time. Right now, there is no continuous time. It is discrete time. So when I say discrete time, it is just samples, okay? Samples, numbers appearing at regular intervals. So the number in succession is simple n, right? This is 0, 1, 2, 3, 4, 5, like that. The first sample, second sample, third sample, like that in the sequence. So the Z transform of that is Z over Z minus 1. Okay, so it's important to remember these basic ones. Now, if you have b to the n, b is a constant, okay, and n is the exponent, right? Say, for example, 2 to the n, right? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, like that, right? As time advances from 0 to 1 to 2 to 3, like that. So rather than saying time, it is the number in succession, all right? So this is the Z transform, Z over Z minus P. And look at the pattern. Z over Z minus 1 is pulse sequence, and all of the pulses are equal length, equal height rather, which is 1, okay? All the samples are 1s here, right? You get this one when you sample the unit step in continuous time. Now, rather than having constant amplitude, right, 1 for all or every n, now you have for different n, different amplitudes, right, different heights. So it is exponentially increasing or exponentially decaying set of samples. The first one is b to the 0. So irrespective of the value of b, the function has value 1. Anything to the power 0 is 1. So then let's say b is 2. 2 to the 1 means 2. That is the second sample. Okay. And third sample is 2 to the 2. Right? First sample is 0. Second sample is 1. Third sample is 2. So 2 to the 2 means 4. So you see it is increasing, right? So when we represent this in Z world, it is Z over Z minus B. B is 2. Okay. So remember that pattern. And there are other things also, right? So we'll come back to this at different times. So today our main discussion is inverse Z transform. Again, we use transforms because we cannot deal with the problem in our normal world or time, right? Time-based world. So when we transform into a different world, maybe Laplace, maybe Fourier, maybe zTransform in this particular case, there we use all the problem, right? And synthesize the solution there. But nobody can understand the solution in that world. So you have to bring it back to normal world, time world, right? Then only you can understand what the solution is, right? So therefore, Z transform is also very important. Inverse transform. So inverse transform is the inverse of the forward transform that we have done already. So therefore, if you know the forward transform, you can figure out the process of inverse transform also. Right. So the mathematically, you write it like that. Now you can see it over here. right? Left-hand side is basically the result of any transform, inverse or forward, right? It's the result or output. And on the right-hand side, you write the input, what goes in, right, to the process. So is it to the -1 means inverse Z transform, and the argument or within bracket, you have the transform, X is it. So any Z transform that you already have, right, when you put it into this operation, the result is the time representation of that. Okay, what sort of time function is actually represented by X is it, right? But this is just a symbolic expression. There's no any mathematical process expressed in here other than the symbolic expression saying that it is the inverse Z transform, okay, which brings from XZ Xn, okay, right. So we are now look at what are the possible techniques to implement this Z-1, right, inverse Z. Now, if you try to connect what we already know, right, this is the transform, the way we write the forward transform, right? You have the set of numbers xn, n from 0 to infinity, and for every such sample, you put z to the -1 together with it, right? For all of the samples, and you combine them together and generate xz. It's a polynomial of z, right? Polynomial of z. Now, if you reverse that one, right? Let's say you get something like this. This is the zTransform of something, right? You get the number and then another number with z to the -1 coming from this transformation. The next two with z to the -2, x3 with z to the -3. If you can see this polynomial, then of course you understand this is the first sample in the time domain. This is the second sample in the time domain. This is the third sample in the time domain, right? Direct inverse reading, okay. All what you need to do is to arrange your Z transform into this format where you have a constant number up front and then plus another number with z to the -1, then plus another number with z to the -2, and so on. If you can arrange your Z transform, which is in a different format, into this format, you can directly read the numbers, first sample, second, third, fourth, and so on. Okay. So that is the easiest way. Now, but in most of the time, you don't get your Z transform like this, right? When you do various operations in the Z world, more often you get your Z transform, which is ready to be inversely transformed to the time domain in this format. What is it? It's not a polynomial, but it's a rational polynomial. Actually, two polynomials, numerator and denominator. This is what you very often get after your process in the Z world. Okay. So now the problem is, how do we get a rational polynomial, right, converted into a single polynomial like this? Okay. If you can do that, then again, you can read the numbers from this polynomial. So this way we are bringing our problem hand to hand, right? We're changing the shape of the problem. Now the problem is, how do we convert a rational polynomial like this into a irrational or non-rational polynomial like this? Of course, this is not very difficult, right? There are techniques to that. There are three techniques. One is the power series expansion method. The second one is actually, we call it recursive method. Recursive method is, in fact, the power series method itself, but formatted in a different algorithm, right? Easy to do that. like code it as a computer program or whatever. And third one is partial fraction expansion, right? So we're going to look at these three techniques as a recap of the zTransform. I think it's very important that you get a very good grip on your mathematics, right, before you can do this module. So that is why I think you need to be ready with, say, a few papers and pen or pencil. Work it out with me, right? Then you will revise what you have already done in the past, recent past. So it is to be remembered that the three techniques, right? Power series, recursive, and partial fraction, in order to convert a rational polynomial into a say single polynomial or partial fractions, right? The first two cases are actually polynomial based. This one is partial fraction based. So these are the techniques that we use to help inverse zTransform process. So let's look at the power series method, right? The problem is to convert this format rational polynomial into the single polynomial format. It's pretty easy. You may have done this very early stages of your academic life, right? Long division. Remember that long division? So we are doing it now, right? Let me demonstrate this with an example. Suppose you have this zTransform, right? 1 plus 2 z minus 1 plus z minus 2 over 1 minus z minus 1 plus 0.3561 z to the minus 2. So now this is your solution in the z world. Now you don't understand what it is, right? Nobody does. So you have to bring this to the time domain, which is inverse zTransform, right? So we'll do the long division. Here it is. The long division, numerator over denominator, right? 1 plus 2 z minus 1 plus z minus 2 divided by 1 minus z minus 1, this one. Right? Take a brief look at it. What you see here is the result. Okay. Now, if you just look at the answer here, now you can forget about the rational polynomial. Just look at this one. The first term is 1. So this is the first sample, right? Like you can see it over here, x0 is 1, right? The first sample. This is the second sample because it comes with z to the minus 1. So find out where is z to the minus 1, right? This is the sample at time 1. Yeah, the sample is 3. So 3 comes over here as the second sample, the first sample, second sample. Then find out the term with z minus 2 is over here. Z minus 2. Get the number 3 point something. And this is x2, which means a third sample in the time domain. And the fourth one and so on. Okay. Pretty easy. So now you understand your solution, right? The way you see it here, right? Nobody can understand what it is. But when you say this is nothing but 1, 3, 3.6439, 2.575, like that, then you can see your sample sequence. All right. So eventually you have to present it like this. So you have the time axis, right? This time it is let's say k, right? k equals 0 over here, the first sample, right, which is 1. Then k equals 2, you are over here. Sorry, k equals 1. The sample is 3, right? It's like a bit taller, 3. Sorry about that. And then the next one is 3.6 something, which is slightly above this one over here, right? This is 0, 1, 2, and so on, right? So all of the samples, this one is 2.57, right? X1, X2, this should be X3, right? Sorry about that. 2.5 something, so it's not as tall as the previous one. So maybe somewhere over here, right? This is the fourth sample. The answer of the inverse zTransform is a sample sequence. Okay. All right. Now, this process, the long division, I'm sure you don't like to do it, right, at this stage. And you kind of figure that out as a child work, right? So to make you a bit happy, let's work it out as an algorithm. Now you at least feel proud about it, right? So same long division given this way. Now you use an algorithm, right? X0, which is the first sample, is A0 or B0. So all what you need to do is figure out what is A0, A1, A2, and so on, which are the coefficients of the numerator polynomial. And then B0, B1, B2, and so on, the denominator polynomial coefficients, right? Now it's all about these A's and B's, all right? So you calculate the first one, A0 over B0. Second sample, you calculate using this equation, right? This is the long division, but concealed, right, in an algorithm. So A1, read from here, A1 minus X0. So substitute to this one, X0, right? Sorry, X0 has already been calculated, which is over here, right? Take it from here, take it from here. Times B1, multiply with B1, divide by B0, this one. So you know where these A's and B's are. It is recursive because once you calculate a sample, you use it to calculate the next immediate sample, right? And then you can see X0 and X1, the first sample and the second sample, they both go in here to calculate the third sample. All right, X1 comes from here, X0 is already calculated. And put it into this equation, A2 minus X1 B1 minus X0 B2 times B0, right? So this algorithm is for any n. This is for X1, this is for 2. What about for n? For any nth sample is calculated this way: an minus summation k from 1 to n xn minus I bi, whole thing divided by b0 for any n, right? And if you just put n equals 1, you can see that you are getting to this expression, right? N equals 1, left hand side 1, x1. This is a1, you can see it over here, minus, you can see minus here, summation I equals 1 to 1, which means just one term, right? Just one term. X n equals 1, sorry, n equals 1 now. So I equals 1 to 1 means x1 minus 1, which is 0, x0. That's how x0 comes into the equation. And b1, okay, only one term. Okay. So this is true for any n. So you can write a little code and give it to A0, A1, A2, and so on. And you know what simple n is. The moment you understand this one, you know what n is, right? And the algorithm will run recursively and get you all of the samples. Okay. Right. So for knowledge, you need to understand these things, but you don't have to do manually long division or even this algorithm. Let's look at this example. Right, I think the same example we worked out for with long division. Remember here, same example. Okay, this time we gonna use the recursive algorithm. So the first thing is to identify the coefficients. Numerator ones 1, 2, and 1. Okay, 1, 2, and 1. So 1, 2, and 1. These are actually A0, A1, and A2. And you see the denominator here, B0, B1, and B2, right? Like that. In this case, capital N and simple M, they're both equal to 2. This is the length of the polynomial. Now here you can see as a record, right? X0 is A0 or B0. 1 over 1 is 1. And then you have x1, which is a1 minus x0 b1 divided by b0, right? So substitute these numbers over here. X0 is 1, which is already calculated, just a previous step. And the answer is 3. Then now you have x0 and x1, which is 1 and 3. Put it over here, right? To calculate x2, which is 3.643 and whatever. So you understand the recursive algorithm, which calculates the first sample, second sample, third, and so on. Okay, right. Let's look at the partial fraction expansion method of working out inverse zTransforms. Again, partial fraction expansion is not new to you, but maybe you need a bit of a revision, right? So that's the whole purpose why I'm doing it at this stage. Partial fraction is used actually to break down a rational polynomial into individual small blocks, as you see over here, right? You can see a long rational polynomial, but once you break it down into this format, like all first order blocks, right, with a constant here, depending on the order. Sometimes you get B, sometimes there's no B, okay? So how do we calculate B? C1, C2 up to Cm, B1, B2 up to Bm, right? That is the question at hand. So once you have the partial fractions, right, you can write it this way. It's a summation of first order terms here, except for B, right? I from 1 to M, C I Z O Z minus Bi. So we write it down this way, right? You can see all of the terms are the same shape, right? Now, if you can write down your partial fractions this format, C1 over 1 minus B1 is equal to minus 1. So this format, right? And M number of them, right? Then once you assemble them together, again, you can go back, right? You can go back to the original rational polynomial that is over here. Okay, pretty obvious. And the other good thing to be noted here is that once you have a block like this, you can immediately work that out through the zTransform, in fact, inverse zTransform, and get to the time function, because this is something we have seen earlier. Forget about this C1, C2, and so on. Other than that, what remains there is Z0, Z minus Bi. Okay, z over z minus b1. Here z over z minus b2 and so on. So if you go back to the z transform table, it is very clear. This is actually b1 to the n, this is b2 to the n, and so on. Can I show it to you? If I go back and remember this one, this format, z over z minus a constant, right? So if you go back to the z table, can you find an entry z over z minus b? This is the entry. If you have this term, this block as a partial fraction, right? The inverse z transform of this one is simply this constant to the power n. So that is why when we do partial fractioning, we have to do it this way, where you create many partial fraction blocks of the same shape, this shape, z over z minus a constant. Okay, right. Now, when we do the partial fractioning, right, there are three possible cases depending on the size of the numerator and denominator. The first case is the easiest, where m is greater than n. M is greater than n. So you can see it over here. M is greater than n, which means a causal system, right? So in that case, b will be 0. There's no b, right? B is just 0. Case 2, m is less than n. It is greater than or equal to n. If m is less than n, right, then you cannot simply do it straight away, right? If m is less than n, if this is smaller than n, you have to do a little adjustment upfront before you can do anything, which is you have to do a bit of long division, in fact, and figure out what is b constant, followed by a rational polynomial which satisfies case 1. Case 1 is where you have a polynomial where the denominator is equal or greater than, right, to the numerator polynomial in order. So once you do, if you have a polynomial, rational one, which has a higher order numerator and lower order denominator, you have to do the partial fractioning first. And then you can figure out there's a constant plus a rational polynomial remaining part which satisfy case 1. Okay, then you can proceed. Then there's another one, not actually a different case. Sometimes you will see multiple poles, right? Here you can see these poles are distinct, B1, this is B2, like that. Sometimes you get the same B here and here. So same pole is repeating. We call it multiple pole case. So if you are in that situation, you have to do an additional steps in partial fraction expansion. Okay. So these are not primarily or exclusively for Z transform anything. This is basically the partial fraction techniques. Okay, right. Now, there's another thing I want to tell you, the basic things to calculate the C coefficients, right? C1, C2, and so on. There's a method called cover-up method. This is that one. I think we discussed this last semester also. The cover-up method is this. You have xz, the whole thing, right? The whole rational polynomial, and you want to calculate C1. which is the coefficient of the partial fraction block, the first block where the denominator is z minus b1, one of the poles of the plant. Okay, the plant has a m number of poles, right? And you want to find out the coefficient of the block with the first, right, pole b1. So then what you do is you put it into this equation, xz divided by z minus pk, the pole, first pole, say p1. Okay, so you work it out and then substitute, evaluate the whole value of this one at z equals that particular pole. Okay, this is very, very simple proof. It's out there on the web, or even you can prove it yourself. I don't want to do it here, taking time. I think partial fraction expansion, I don't remember whether I worked it out with you last semester. But anyway, it's a pretty simple, straightforward method. In few steps, you can work it out. So all of the C's can be calculated like this. So when you have multiple poles, right? Only difference is that when you have a pole repeating twice or three times, right? You get new terms in the partial fraction expansion formula, this one. If one of these poles repeating, right? Say z minus b2, it repeats two times, right? You just can't say this is z minus b2 whole thing square or something, right? So you have to write this one anyway, plus another term, right? Which is given like this. Only for repeating poles. And the multiplicity is m. Let's say there's a pole repeating twice, m equals 2. Then you have two terms. You have two terms here in this sequence, right? If there's a pole which is repeating three times, there are three blocks, right? Not just one or two, three blocks. The number of terms in the expression is equal to the multiplicity of that particular pole. I'm just revising, not actually teaching anything new to you. I think I'm doing this because you might have forgotten these basic math. Okay. So when they're repeating, you get coefficients for, so each term you get a coefficient d1, d2, d3, and so on. So these coefficients are calculated using this equation, right? Kind of lengthy, but you don't have to worry. As long as there's a mathematical equation, you can use it, substitute, and then calculate your d's. All right, so that's the additional work you have to do when the poles are repeating. Okay. All right. So with that, we can actually look at an example. What about this? By the way, before we proceeding with the example, any questions up to now? All right. So now here we have zTransform. Hz is equal to 1 minus z minus 1 over 1 minus z minus 1 minus 6 z minus 2, right? So nobody knows what it is, okay? So we have to bring this back to the time domain, right? We know it's a sample sequence. So what is the first sample, second, third, and so on, right? Okay, so based on what we have learned up to now, this is the numerator polynomial, the denominator polynomial, and obviously m is greater than n. This is higher order than this one. So this falls into case 1. We know what case 1 is. Case 1 is where there's no b is 0, right? This one, b is 0. Then we break this down to two partial fractions, and we know denominator 1 minus z minus 1 minus 6 z minus